I'd like to refresh you guys on the CP, which is the heat capacity at constant pressure. Okay, we have mentioned about the equation, the polynomial equation, which you can get from Appendix B2. That's the sorry, let me get this figure. Okay, that's the equation from Appendix B2. And if you happen to have a mixture, that mixture you can use this equation. Yeah, that this mixture you can use that equation, and that equation is valid when you have gases. It gives a very good approximation when you have gases, and when you have similar liquids. That means the liquid, they are similar in structure. For example, you have uh, you have hydrocarbon. Okay? They are the same hydrocarbon, so it's similar. But if it's not similar, then your approximation will be quite far off. Okay? It will not give you a very good approximate. So you can use that equation where you have this is mole fraction. I did mention that last time. Okay, let's look at an example where we can apply the equation. Let me see. We're going to use this example. Okay, over here in this example 834, let's read through it. You need to calculate the heat. You have 150 mole per hour of a stream. It contains 60% of ethane, 40% of propane. Both are gases. You're going to heat it up from 0 to 400 degrees C. There's no change of phase at all. It's just heating and cooling. In order to solve this problem, this question required you to get the heat capacity of the mixture. So that's using the equation that I just mentioned just now. But I'm going to solve it differently. But I will also mention about the heat capacity of the mixture. But I'm going to solve it differently from the textbook so that we can see whether we're going to get the same answer or is it going to be different. Okay, so let's handle this. Let's draw the diagram first. But before looking at this, I need to go back to the notes, which is about the regarding the procedure for energy balance. I did mention that last time. Okay, this is the procedure. Let me erase this. We have done the few examples before this, whereby we have used this procedure, but it's just that I did not went through it step by step. So the first step that you have to do is you do the material balance. You do the material balance, and you have to write your basis. I did mention this last time. You need to write your appropriate energy balance equation. If you're having a closed system, then you have your internal energy. If it's an open system, you have the enthalpy. You just need to know what system you are dealing with. Okay, write the full equation. Do not simplify it yet. After that, you need to draw your before you go to the first step. Remember, you need to draw your diagram first. You need to draw your diagram because you might, having the diagram done, it will make it easier for you to solve it. And after you have done the second part, which is the equation, from there you will know what terms you need to cancel from the question itself and also from your diagram. You should kind of know what terms to drop off from the general equation. And before you carry on with your energy balance, you need to have a reference state. Whenever you have a reference state, please write down the phase, liquid, gas, or solid, the temperature that you're going to choose as your reference temperature, and the pressure that you're going to choose as your reference temperature. So you need to specify these three terms, these three things, which is phase, temperature, and pressure. Normally, I did mention this yesterday, if you have a table that you can get your data from, then your reference state must be the same as that table. But if it's not available, you have a choice of either using the inlet or the outlet condition as your reference state. Okay, we will continue to the next step. You need to construct yourself a table. Okay, you need to construct yourself a table. But for the yesterday, when we did the example yesterday, we did not construct the table because you only have one component and one phase. For example, in this table that I have over here, you have I think that is what is AC. AC is it acetone. There's two of it. One of it is vapor. The other one is liquid. So you're going to have it listed as vapor and as liquid. You cannot combine the two of them together. Okay. So it's going to be two on the vapor in the top row and the liquid on the second row. And after that, another component, which is nitrogen on the third row. So you need to construct yourself a table. You have your inlet molar flow rate, your outlet molar flow rate, your enthalpy in and enthalpy out. Please take note of the unit, because some enthalpy, if you look at the steam table, the enthalpy will not be in kilojoules per mole, but it will be in kilojoules per kilogram. So you get to note down the unit of your enthalpy. Okay, take note of the unit of your enthalpy. Okay, calculate or get the data of your internal energy or your enthalpy from the appendix, or you can calculate by using integration. We have done that. Okay, or if there is any phase change, then you might have to use your hypothetical path that we have gone through. We have gone through how to use your hypothetical path in order to calculate the enthalpy. Okay. Any terms that need to be cancelled off, for example, kinetic energy, work, or potential energy, give the reason for dropping it off. Do not just say it's equal to 0. You need to specify why it is being dropped off. Okay? Then you can solve the energy balance based on what you have written in the table. Your energy balance, you can easily get it from the table and solve it. Okay, now let's go back to that example just now. Okay, now we have this example. Let's draw the diagram. The first step is to draw the diagram. We have an open system whereby you have a stream that contains two components, 150 mole per hour of 0.6 mole per mole of ethane, and the rest 0.4 mole per mole of propane. That since there's only one inlet and also another the outlet is only the same stream coming out. There's only one outlet, so it's going to have the same molar flow rate and the same composition. Nothing going to change regarding that stream. It's just coming in and out, but it's just heating up from 0 degrees C, write down the temperature from 0 degrees C to 400 degrees C. Make sure you write down everything that is given in the question, that is stated in the question. So write down everything so that you do not miss anything. Okay. So now the question is for the amount of heat that you need to put in Q. And there's no mention of whatever unit, but based on the answer here is kilojoules per hour. So it's going to be kilojoules per hour. Okay. So the first part of the question state that you're going to use heat capacity of the mixture. So just now I did mention about the equation. The heat capacity of the mixture equals to the summation, the Y, which is the mole fraction of component I, times by the Cp of that component I. So since we have ethane and propane, so we're going to use this example. Your ethane, the mole fraction is 0.6. So get the heat capacity of ethane. The mole fraction of propane is 0.4. So multiply that with the heat capacity of propane. So let's look at our table B2. Here I have ethane. That's ethane. So this is A times 10 to the power of 3, B times 10 to the power of 5, C times 10 to the power of 8, that's D times 10 to the power of 12. So I'm going to use these values for ethane. So it's going to be 0.6 bracket. Let's look at the value, 49.37 times 10 to the power of negative 3 plus 13.92 times 10 to the power of negative 5. Remember, there's a T temperature term there, minus 5.816 times 10 to the power of minus 8 T to the power of 2. And lastly, your D, 7.28 times 10 to the power of negative 12 T to the power of 3. That is your CP for ethane. Okay, so that's what I did. So now let's, for propane, I'm going to use a different color. Okay, green. That's propane. So this is A times 10 power 3, B times 10 power 3, 10 times, B times 10 power 5, C times 10 power of 8, and D times 10 to power of 12. So I'm going to write the whole thing all over again, but this time I need to plus it, multiply it with the mole fraction of propane. Propane is 0.4, so multiply it with the mole fraction of propane. So let's look at the values, 68.032 times 10 to the power negative 3 plus 22.59 times 10 minus 5. Again, there's that T term there. Minus 13.11 times 10 to the power minus 8 T square and 31.71 plus 31.71 times 10 to the power minus 12 T to the power of 3. So you need to multiply it. And I'm not going to do the calculation. I'm just going to go straight into the solution. This is going to give you 0.05683 plus 17.39 times 10 to the power of minus 5 to the T minus 8.734 times 10 to the power of minus 8 T square and plus 17.05 times 10 to the power of minus 12 T to the power of 3. So that's the final equation for the mixture. This is for the mixture which contain ethane and propane. So if you want to continue this problem, you need to first before you do anything, I forgot about the basis. Have the basis. The basis is 150 mole per hour. Have the basis. And if you want to continue this energy balance, have your reference state. State your reference state. So what is your reference state, guys? What is your reference state? What reference state are you going to use?
The inlet or the outlet?
Yeah, choose one of it. Okay. So let's choose, for example, because the inlet is at a lower temperature. Let's choose that as our reference state. So we need to specify the component. So there's two components here. You have ethane, the phase gas, and then you have propane, and both of them are gases. Write down the phase, the temperature 0 degrees C, and the pressure. Since there is no mention at all about the pressure, so we're going to assume it's going to be at 180 M. Yeah, so that's your reference state. So now, once you have got your reference state, since it only involves a change of temperature from 0 degrees C to 400 degrees C, there's no mention at all about any change in pressure. There's no mention about any change of phase. So it's just heating up. So whenever there's just a change of temperature, then you'll be dealing with the integration of the heat capacity. So let's write the equation. We have an open system. Your open system, the equation is going to be delta H, which is enthalpy, change in kinetic energy, change in potential energy is equals to heat plus shaft work. So we know that there's no kinetic energy change, there's no potential energy change, and there's no shaft work, based on the fact that there's no change in velocity for the kinetic energy. There's no change in elevation or height, and there's no moving parts, no turbines, no pump. So we drop off these terms. We end up with heat is equals to the change in enthalpy. And that, if you expand it, is going to be out the molar flow rate times by the specific enthalpy minus summation the outlet or inlet, the molar flow rate times by the specific enthalpies of that inlet stream. So that, since we stick it with that equation, this is our final equation. So we're going to use the first method. I'm going to use the first method, which is using the heat capacity of that mixture. I'm going to use this method using the heat capacity of that mixture. So my heat capacity of that mixture will be the same for the inlet and the outlet. The heat capacity of that mixture is going to be the same for the inlet and the outlet because they are both the same mixture. So this is in and this is out. So what is the enthalpy of your inlet stream, guys?
0.
0, yes, because
It's the reference state.
it's at the reference state, yeah. Because you choose your inlet as your reference state, so automatically that enthalpy is going to be 0. Now you need to calculate the outlet enthalpy. Give it a unit, write down the unit, kilojoules per mole. Right? So we're going to use the Cp that we just obtained just now for that mixture to calculate your outlet enthalpy. So your outlet enthalpy is equals, let me write the whole thing first. I need to erase that. Okay. Your delta H is equals to your outlet minus inlet. Okay. So your inlet just now we say is going to be 0. So you end up with just the outlet and the enthalpy of the outlet. And that is going to be an integration of your Cp for that mixture with respect to temperature. So what is the starting temperature for the integration? Anybody? Let's look at the diagram.
0.
Zero.
Yeah, 0. You start from 0, you go to 400. So your starting will be 0 degrees C and your final will be 400 degrees C. But have a look at the unit we're going to use. Is it degrees C or is it Kelvin? Okay, it's going to be degrees C. Right, so we're going to use degrees C, and the equation that we're going to use is in the form of equation 1. I automatically write it down just now without mentioning of the form, but take note of the form of the equation. So now all you have to do is jot down the Cp that you just got just now based on the mixture, based on the mole fraction, the sum of the mole fraction. So that is going to be 0.05683. I'm going to just rewrite the whole thing. So you guys can already plug in the numbers in your calculator and see whether you're going to get the same answer as the solution inside our textbook. Oops. dt, I don't have enough space to write dt. Okay. See whether you get the same answer as that in our textbook. Where's my textbook? Okay. What did you guys get? I'm not going to plug in the values. I'm just going to give the value given, write down the value given in the solution of the textbook. Kilojoules per mole. Did any of you guys get a different value? Anybody? Anybody getting a different value? Or all of you guys managed to get the same value?
I got the same value, Doctor.
Same.
Same.
Good. Thank you, Muhammad Ikmal. Okay, assuming that everybody managed to get the same value, so now we will continue with the calculation for the heat, which is using, let me see, I'm going to change this, I prefer red. Yeah, using this equation. Yeah, I'm going to use that equation. So, putting in the values, let me take that, okay. Q equals to out molar flow rate minus in. I'm actually repeating the whole thing all over again. Okay, so we have the same number of mole. How was the number of mole? In our diagram, the number of mole is 150. So the number of molar flow rate is 150 mole per hour. So you can actually take this out. H out minus H in. Yeah, so I'm going to write down our out value, the enthalpy of the outlet, 34.89, minus the enthalpy of the inlet, which we already specified as 0 because it is at the reference state. That's kilojoules per mole. So cancel off the mole. You will end up with kilojoules per hour. Okay. So what's the value? Let's have a look from the solution. The answer is 52. Is it? No, it's 5,230. Check your calculation, please. I'm not going to do the calculation. I'm not going to plug in the values inside my calculator. I'm just going to give the values for the answer from the textbook.
Said 4 plus 5 equals
See whether you get the
6.
same answer. Anybody getting a different answer, please give that answer so that maybe we can check.
5233.5,
said
Doctor.
hello.
5233.
0.5, yeah.
Thank you. So that the answer from the textbook is not right, isn't it? Or is it they round it off?
Yeah.
5233.5.
Off.
Yeah, they round off the value.
Loba said Ikmal.
So this is the answer we get if you use the equation for the CP of the mixture. Now I'm going to redo this same example. I'm going to redo it using the table that I just mentioned to you guys just now. Okay, I'm going to tabulate it in a table. I'm going to have, since we have two components, I'm going to have two rows. This is ethane. This is propane. This is my, oh my god, I cannot even get it straight. Try to get it straight. Okay. Okay. That's roughly. So N in, the unit is going to be mole per hour. Enthalpy in, kilojoules per mole. I'm going to do this differently from from what we have just done. Mole per hour and enthalpy out. I got it wrong here. That's out. Oh dear, my god. I canceled that. Okay, that's out. Yeah, that's out. Kilojoules per mole. Okay. The number of mole of ethane coming in. This is the good thing when you draw your diagram. You know what's the value. What's the value of ethane coming in, guys?
90 mole per hour.
How did you get that?
90 mole per hour.
I know, Ayman, it's 90 mole per hour, but how did you get that 90 mole per hour?
Multiplying the total molar flow rate by its composition.
Okay, which is propane or ethane? Which one? Ethane.
0.6.
Okay, 0.6 times 150. So that will be 0.6 times by 150. So if you do the calculation, it's going to be 90 mole per hour. Okay? So the rest of it is for propane. So 150 minus 90, that would be 60. Is that correct?
Yes.
Okay, good. Thank you. So the same amount of mole will be in the outlet because nothing goes, there's no mixture. I mean, there's just one stream coming in, one stream going out. Nothing, there will be no change in the molar flow rate. Okay, now I'm going to use a different method. Okay, I'm going to use the same reference state as before. reference state as before is going to be the same. I'm going to have propane, gas, ethane, propane, still the same, at 0 degrees C, which is the inlet, and 1 atm. The only difference is that I'm going to do the calculation of the CP individually. I'm not going to have it as a mixture. So what I'm going to do is I'm going to do it separately. Okay, I'm going to do for ethane the same value of the CP that we just got just now. Okay, this is the CP of ethane. Okay, that's the CP of ethane. I'm going to get that and I'm going to integrate just that CP for ethane. So let me write down for ethane. Ouch, sorry about that. What is the inlet enthalpy for both components, guys? What is enthalpy in for both components?
Zero.
Good. Because we already specified that both of them is at the inlet. The reference state is the inlet condition. So that's 0. So now I need to calculate this value and that value. Okay. So H1 is equal to the integration from 0 degrees C to 400 degrees C. And H1 is referring to ethane. So I will be looking at the enthalpy, looking at the heat capacity of ethane, the one that I just, this value. Yeah, the whole thing. So 49.37. Going all over, I'm going to repeat myself. Times 10 power of negative 3. Plus, let's look at the appendix. 13.92. I'm scrolling up and down here. 13.92 times 10 to the power minus 5. Remember the temperature term. Next is minus 5.816. Okay, minus 5.816 times 10 to the power minus 8. For those who already got this listed down, why don't you try to get the value of the integration for ethane plus 7.28 times 10 to the power minus 12, T to the power of 3. Oh dear, I don't have enough space. It's going to be dt. Okay, so that's 3. So what's the answer, guys? Somebody try to get it. I will do the same thing for propane. I'm going to look up the appendix B2. And for propane, it's this value. That's propane. Okay. Is 68.032 times 10 power negative 3 plus, I'm going back to my equation, 22.59. This is obtained from appendix B2, guys. So you should be familiar now with the equation times 10 to the power minus 3 times 10 to the power minus 5 times 10 to the power minus 8. So you should be very familiar with it now. Minus 13.11 times 10 to the power minus 8 T square. And the last term, the D part, is 31.71. Plus 31.71 times 10 to the power minus 12 T to the power of 3 dt. So please, guys, give me the values for enthalpy 1. What is it? Somebody calculate for me the enthalpy 1. After I have done it, whether you guys get the same value, let's see. The answer I got is 29.69 kilojoules per mole. Did you get that?
Yes, doctor.
Good. Thank you. For the second enthalpy, H2, when I did the calculation, I got 42.69 kilojoules per mole. Anybody getting the same value? Okay, please, my calculation.
Yes, doctor.
Yes, thank you. Okay, what happened there? Okay, that's going to be 29.69 and H2 is 42.69. Okay. Everything is there. We have completed our table. We have filled up everything. So now what you have to do is just continue with the solving the equation using this equation, solving the energy balance using that equation. Okay. So right now we cannot use this part of the equation. We cannot use this part of the equation because we have two components. It's not only one, it's two. So we're not going to use that part. We're going to use just this front part of the equation. So let's solve that problem using the table. So Q is equal to summation out the molar flow rate and its corresponding enthalpies minus the inlet, the molar flow rate times by the corresponding enthalpies. So what we have over here, the outlet. So the outlet is this times by its enthalpy. And then I'm going to change it. I'm going to change using, okay, that value times with its enthalpy, corresponding enthalpy. So let's do that. 90 times 29.69 plus 60 times 42.69. That's your outlet. And what is your inlet, guys? What is the sum of the molar flow rate with the enthalpies of the inlet?
Zero reduction.
0, because whenever you multiply anything with a 0, it will end up being 0. Okay, so that will be 0. But if you want to write it down, it's no problem. Just write it down, minus 90 times by 0 plus 60 times by 0. So what's the answer? In kilojoules per mole. You know the unit is going to be kilojoules per mole because we just did the, the unit should be kilojoules per hour, not per mole. Because we did the calculation previously using the mixture, the enthalpy of the mixture. The answer is kilojoules per hour. So let's do the calculation and see whether we're going to get the same answer as what we got previously. Is it going to be 5,233.5? This thing, I can actually bring it over there. This whole thing, bring it over there. Okay. So what's the answer? What is the amount of heat that need to be supplied or transferred into your stream?
Same answer, Doctor.
Good, thank you. So you have two ways of doing this problem, 5,233.5. Thank you very much. So I have shown you guys two ways of solving this problem. You can either use the CP of the mixture, the heat capacity of the mixture, which is using the equation, this equation, or since we are dealing with gases, okay, they are gases, you can also use the individual CP of every component in that mixture. And if you do that, you need to tabulate your table. You need to construct a table and fill up the table. Which one is easier for you guys? You just, you choose which one you find easier. Then you will come up with the same answer. Either method will give you the same answer. So it's just a matter of choice. Okay, guys?
Yeah, Doctor, I've got a question.
Yes. What's question?
What if I take the state 2 as reference state? The answer would be reverse or negative.
Yes.
So like in exam, should we be instructed in like what state to take or what? Because the answer will be completely different. Negative or positive.
Yes, but then it makes sense, isn't it? If you're going from a higher temperature going to a lower, from a higher temperature going to a lower temperature, definitely you're going to release heat, isn't it?
Yes, true.
Yes. So, the person who is going to grade the equation should know that going from a higher temperature to a lower temperature will give off heat. It's just common sense. But then, look, from the question itself, you're going to go from 0 degrees C to 400 degrees C. So if you choose the outlet as your reference state, you know that the question asks from 0 to 400. So you know what you have to rewrite your answer.
Okay, got it.
Okay. Any other questions? Anybody? Any other questions? No questions? Okay, good. Let's do the next example. We just did just now example 834. How about looking at 835? Let's see. 836, 835. Okay. Wow. Let's read through the question. You have a stream. Again, you have a mixture. 10% methane, 90% A by volume. So if you change that to molar percentage, is it going to be the same? This is percent volume. Are you going to get the same percent mol, guys?
Yes.
Good, thank you. Now you're going to heat it up from 20 degrees C to 300. This question is very similar to the previous example, but your flow rate is not given in mole per hour or mole per minute. It is in liter per minute, liter at standard temperature pressure. Yeah? There's no mention at all about the molar flow rate here. It's just the volumetric flow rate, but at standard temperature pressure. So there's a slight difference. Sometimes this small slight difference will really affect on how you're going to solve the problem. You need to find the heat that need to be input in kilowatt. That's the question all about. So first thing first, before you do anything else, draw your diagram. Oh dear, if only I can just skip this part. I don't want to do the, yeah, I'm going to cut this. Yeah, I'm going to cut this. Okay, there's a lot more space now. Okay, you have you have your diagram. You need to draw your diagram. This is a stream. There's a stream coming in and there's a stream going out. Same diagram. You have your 2 times 10 to the power of 3 liter at standard temperature pressure per minute coming in. So that same value will be coming out. Your mole fraction 0.1 mole per mole of methane, and the rest will be your mole per mole of A. Yeah. So the temperature coming in is at 20 degrees C, and the temperature going out, you're still going to have the same mole composition. Nothing changed. 0.9, just repeat it. Repeat all over again. Your A, and the temperature is 300 degrees C. Okay. So now, the question asks, what is the heat that you're going to put in kilowatt? Okay. When we did the previous example, you know that your heat capacity, you will get it from Appendix B, Table B2. Sorry, yeah, B2. If you're going to get your CP, okay, you're going to use that CP, the unit will be in kilojoules per mole. Definitely, you cannot use this flow rate because you cannot cancel the unit. So we need to change that volumetric flow rate into mole per minute. So how to do that? You are given the statement standard temperature pressure. At standard temperature pressure, that means the temperature is going to be 25 or 0 degrees C. Guys? Standard temperature pressure?
25.
25, okay. 25 degrees C. And what's the standard pressure?
1 atm.
1 atm. Thank you. Yeah. At 25 and 1 atm. So you sure? You sure 25? Check.
273 Kelvin. Yeah, it is true.
Standard temperature. What is standard temperature? Are you sure it's 25?
Yes, yes.
Yes, doctor. I think so.
Yes, doctor.
Okay, good. I just want to check because I'm not sure myself. Okay, so at that standard temperature pressure, your number of molar flow rate, the volumetric, volumetric specific volume should be what? Specific volume. Anybody? Liter per mole. What is that value? The value, liter per mole. Anybody? Do you know? 22.414 liter per mole. You can check that up. Yeah. The specific volume at standard temperature and pressure. That's the value. So now, knowing that, you're going to change your volumetric flow rate, which is 2 times 10 power of 3 liter at standard temperature pressure per minute. So you're going to use that 22.414 liter per mole. When you cancel that, you're going to get mole per minute. You're going to get mole per minute. So that answer, after you have done it, you're going to get 84.6, is it? Is it 84.6? No, it's not 84.6, isn't it? What's the answer?
89.23.
89.23. Anybody getting a different value? Thank you. Thank you, Ibrahim. Anybody getting a different? Same. Okay, good. Okay, now, my question is, why is it that this temperature is specified and yet this temperature is, this is given as STP? Is there a difference in the temperature? Why is there a difference in temperature? We just said that the standard temperature is at 25, but here it says the temperature is at 20 degrees C. Why is there a contradiction?
Well,
Anybody? Anybody?
I don't know. Well, maybe the
I think
pipe
STP
itself
is
at 25 degrees C.
What is at 25 degrees C?
Maybe there is like this flow rate flowing through a pipe. This pipe at 25 degrees C.
Okay. Anybody disagree with that?
Mm,
Or anybody agree
I'm
with it?
not. I think STP is 25 degrees Celsius, referring to the room temperature. if I'm not mistaken.
That's Faisal's opinion. Okay, guys. The actual stream is actually at 20 degrees C. The actual stream. This standard temperature pressure is only referring, it's not referring to the actual stream. That molar flow rate, it is only referring to that molar flow rate at standard temperature pressure. But the actual stream is at 20 degrees C. It's not at standard temperature pressure. But the molar flow rate is at standard temperature pressure. That's what it means. Okay? Your flow rate is at standard temperature pressure. If it is at standard temperature pressure, then that is the molar flow rate. But the temperature, the actual temperature is as given at 20. Okay? That's why there's two different temperature here. The molar flow rate, if it is at standard temperature pressure, that is the value, 2 times 10 power of 3. But the actual stream is not at standard temperature pressure. The actual stream is at 20 degrees C. Okay, guys? Does that make sense? Nobody?
Yeah.
Okay, good. Okay, now let's continue. We have a mixture of methane and A. So now, basis. What is your basis, guys? What's your basis? You can use the molar flow rate as your basis, or you can use the number of mole that we just calculated just now, mole per minute of mixture input fat of the mixture fat. Yeah, that is your basis. You can use the volumetric flow rate as your basis. No harm. You can do that. Either one. Okay. So let's continue. You have already drawn your diagram. You have already stated your basis. The next step would be to write down your energy balance. You are looking at an open system. Again, the same equation as we have wrote in the previous example. The change in enthalpy plus the change in kinetic energy plus the change in potential energy is equals to heat plus your shaft work. Again, we're going to assume there's no shaft work, no potential energy change, no kinetic energy change. Give the reason. I'm not going to write down the reason, but you know what to do. Okay, so you end up with the final equation. The heat rate of heat transfer is equal to the rate of enthalpy change. And if you expand that, outlet molar flow rate specific enthalpy minus inlet molar flow rate specific enthalpy. Yeah. Okay, now, again, you have two components here. What is your reference state? I'm going to give you guys a different method of doing it because the method in the textbook uses the specific enthalpy and both components will be at the same reference state. Okay, if you look at your textbook, let me look at my textbook. Example 3835, the reference state is methane and A. Okay, they use, okay, that's what I'm going to do actually. That's the same thing. Okay, I'm going to use the same reference state as the textbook. Sorry. Okay, you're going to have methane gas at the inlet condition, 20 degrees C, 1 atm. Okay, that's one. And your A is also gas. You're not going to have it at the same temperature as your methane. Why? Because you can easily get your enthalpy from the appendix B8. So looking at that appendix, you're going to use the same as that of B8. So let me go back to my appendix. Yeah, B8. We're going to look at B8, appendix B8. So this, we need to scroll up. Where is B8? Oh, there, that's B10. I miss it. Where is B8? That's B8. Okay, that's B8. Yeah, you have A over here. That's A. But you don't have methane over here. Okay? So your reference state will be 1 atm, 25 degrees C. What gas? You're going to specify it as A, not just write gas. It has to be A because that component is the one that you are looking at. If you just specify gas, it could be any gas, any gases. It could be oxygen, it could be nitrogen, it could be water vapor, anything. So you need to specify the component is A. Okay, the component is A at a pressure of 1 atm and the T reference is 25. So let's go back to that example. Your reference state is A, gas at 25. Oh, sorry, I need to use this. Let's erase that. 25 degrees C, 1 atm. Okay. You have two components, two different reference state. You can do that. You can do both of them at the same reference state. It's up to you. If you choose both of them at the same reference state, for example, you choose the inlet for both components at the same reference state, then you will have to use for A the CP from appendix table B2 because you're not going to use appendix B8. You're going to use the CP from appendix B2. If both of them is at the same reference state, both of them is at that reference state, your inlet. Okay, so now let's do the table. Let's tabulate our table. You have two components again. You have methane, you have A. Let's see whether I can get a straight line. That's the inlet, that's the inlet, that's the outlet, that's the outlet. Okay. Let's see. Partial. To tidy up a bit. Okay. Okay, now fill up your table. And in is going to be, the unit is going to be in, what is the unit? Mole per minute. Mole per minute. Okay, enthalpy in going to be kilojoules per mole. And out, mole per minute. And enthalpy out, kilojoules per mole. Okay, done. So we just now obtained the total flow rate. The total flow rate that we got just now is 89. Yeah, that's 89. You need to multiply it with the mole fraction of the methane and the A. So just like what we did just now in the previous example, we're going to do the same thing. 0.1 times by the total flow rate, 89.23. Yeah, and 0.9 times by 89.23. So give me the value for this value. It should be 8.923 and sorry.
8.923, yes.
Yeah. So that's easy. For the other value, please, for A.
80.81. 307.
80.30. Thank you very much. Thank you. Okay, now, what is the enthalpy for methane? The inlet enthalpy. Inlet enthalpy. For methane. What is this value?
Zero reduction.
0. Because that is our reference state. We choose it as the reference state at 20 degrees C and 1 atm. Yes, that's going to be 0. What is the enthalpy for A, for the inlet? Is it going to be 0?
No.
No.
It's going to be at that condition.
Yes.
The temperature of 20.
Sorry? The enthalpy, Sulaiman, what did you say just now?
I mean, it's going to be at that condition of 20 degrees Celsius. The one we just...
We get it,
Okay, so
we get
what's...
from 7B8, right?
Yes. It's not going to be 0, guys. It's not going to be 0 because your reference state is not at the condition of your inlet. It's not at 20. Your inlet is at 20. This is at 25. So it's not going to be 0. So let me erase that. It's not going to be 0. Oops, I erased the whole thing. Oh my God. I should have a line there. Okay. So let's go back to our appendix. Your temperature just now is at 20. It's somewhere here, 20. It's between. So you need to get that. You need to do the interpolation. What is that enthalpy? So let's get down. Let's look at the unit. Sorry, not the unit. The value. You have 0 minus 0.72 at 25 is 0. Okay, I just need to remember 0.7 negative 0.75. Yeah. Let's put it over here. Temperature, degree C, you have 0. You need it at 20 and 25. Your enthalpy, the unit is kilojoules per mole. That is your temperature. Here is 0. This one just now. Anybody? Can you remember? I just forgot.
Negative 0.72.
Thank you. That is the problem with getting all the negatives. Sorry, can you put 7 point?
Negative 0.72.
Yes, thank you very much.
And
okay.
The interpolation, I got negative 0.144.
144. Okay, thank you. Thank you, Aiman. So that is your enthalpy. Give it a value of, you could write the symbol if you want. If you don't want, then just erase that. Okay. Going to erase that. That, you don't want that. Now, that's going to be 0. That is 0 point negative. There's a negative sign there, 0.144. Yeah, 0.144. Now, for the outlet, you're going to have the same molar flow rate, same value, nothing changed. Now, for the second, for A, the outlet of A, the outlet temperature is 300 degrees C, 300 degrees C. Yeah. So we're going to get the enthalpy of A at 300 degrees C. Again, you're going to refer to that appendix at 300 degrees C. So if I use this marker, that's 300, that's 8.17. You don't need to interpolate because you can read it off directly from the table, from the appendix. So that's 8.17. So let's go back to our table, 8.17. Now, what you need to do is to calculate this value, the enthalpy for methane. Okay, you start your reference state at 20. So if you do the integration, you will start at 20 because your reference state is at 20. And the final temperature that you want to get is equals to, let's see, write down that outlet is equals to final temperature is 300. And your CP for methane. What is the CP of methane? Let's have a look at our appendix. B2, we need to go to appendix B2. B5, that's B5. B4, B3, okay. Now it's almost B2. Okay, that's it. We need for methane. We need to look methane. Okay. I saw methane there. That's methane. Yeah, it's gas. Yeah, liquid. Sorry, not liquid. That is first form. We're going to use degree Celsius, not Kelvin. If you're going to use the other equation, it will be using Kelvin. You have the second equation, not the second equation. You have the second row there. This is in degree C. This is the value of the A, B, and C and D that we're going to use for our polynomial equation. Yeah. So you guys, you need to write that down. I'm going to have a hard time writing it down because I need to flick through. Let's see, it's 34.31. Ouch, I keep doing this. 34.31 times 10 to the power minus 3 plus, I'm going to flick through again because I'm having a hard time remembering it, 5.469. 5.469 times 10 to the power negative 5 temperature term. Next,
0.3.
Sorry?
0.3661.
Okay, thank you, 0.3661. I'm having a hard time remembering 3.3661 times 10 to the power minus 8 t squared. And what's the last value, please?
11 times 10 to the minus.
Is it minus?
Minus 11. Minus 11.
No,
Okay.
plus minus 11.
Yes, I think so.
Okay.
Okay, let's check. Let's check. Minus 11. Okay, minus 11. Right? Minus 11 times 10 to the power minus 12 t to the power of 3. Close the bracket dt. Yeah, so now do the calculation, guys. What value will you get? Let me see whether I have it done.
I got 12.07.
12.07. Okay, 12.07. The unit will be kilojoules per mole. Thank you. Okay, so now putting in that value over here, let's erase the question mark. That will be 12.07. You have completed the table. Okay, so now all you have to do is calculate your heat loss based on this equation. Based on that equation. Yeah, just like what we did just now in the previous example. Heat loss is equal to summation out. I'm repeating myself all over again. By now, everybody should know this equation, but you should already memorize it by heart now. Right, so that's out. So let's look for methane. What did I do? I got the wrong. Okay, that's methane. Time by its corresponding enthalpy. 8 volts. My God. 8.923 times 10 12.07 plus the value for A, so that's A and its corresponding enthalpy, so 80.307 times by the corresponding enthalpy, yeah, that's the outlet minus the inlet. Your inlet, now we're going to look at the inlet. We have for methane, and that's its corresponding enthalpy. So it's 8.923 times by 0 plus for our A and its corresponding enthalpy. So that's going to be 80.307 times negative 0.144. So now do the calculation. What will be your answer, guys? Let me see. What is the answer in the textbook? The answer from the textbook, we need to change it into kilowatt. The unit just now is kilojoules per mole, times by the molar flow rate. The molar flow rate is mole per minute, so your answer will be kilojoules per minute. Kilojoules per minute. So that you need to change it to second. 1 minute, 60 seconds.
Doctor, I got 678.8 kilojoule per minute.
678.8.
Yes.
Thank you. So if you divide that by 60, what will you get?
Sorry. I got 11.31.
11.31. Slightly different from the answer in the textbook. Yeah, that's our answer. The textbook give a value of 12.9 kilowatt. This is kilowatt. Yeah, we cancel that. It's kilowatt. The answer is different. Why is there a difference in value? Let's check our enthalpy that we get. The H1 in the textbook, they managed to get 12.09. Okay, we got 12.07. That's still okay. The H2, the textbook managed to get the same value, H3, same as us. Okay, for H2, 0.15, negative 0.5. We got negative 0.144. That's slightly off. The value inside the textbook is negative 0.15. Maybe that's the reason. Another reason is this value. The textbook give it a value of 80.4. This value also is different. Inside the textbook is 8.93. So that's where the differences are because of the rounding off done by the author. Okay? So that's why our value and the textbook answer is not the same. Any question, guys?
Doctor, I got 12.9 kilojoule per second.
Oh dear. You got 12.9.
Yeah.
12.9 kilojoules per second. No, that is 12.9
Kilojoules per
kilowatt.
second.
Kilowatt? Kilojoules per second. Yeah.
Kilojoules.
Yeah.
I think kilojoules per second equals 1 kilowatt.
Yeah,
1
I
kilojoules
think-
per second is
I
equal
think
to 1
yes.
kilowatt. So basically, it's the same.
Yeah. So it's the same now with the textbook. 12.9. Yeah. Okay. Somehow we managed to get the same value. 12.9. Any question, guys? This example and the previous example is the same. The only difference is that you need to change your molar flow rate, your volumetric flow rate, which is in standard temperature pressure, into molar flow rate. That's the only difference. Previously, you have the molar flow rate given. Now, you need to change it from volumetric flow rate using standard temperature pressure to the molar flow rate. That's the only difference. Okay? The procedure is the same. But I need to point out, whenever you have the component listed in the appendix, the enthalpy is given in the appendix, try to use that appendix to solve the problem. It will save you lots and lots of time instead of integrating it. Okay? Any questions? No? No questions? Okay, good. That means I hope everybody understand it. So now let's look at another example. We're going to we look at example 836. Wow, this is a very long statement. You have a gas stream. You have 8% mole carbon monoxide, 92% mole carbon dioxide at 500 degrees C. We're going to put it to a boiler. A boiler is a heat exchanger. So this is your hot gas, 500. That's your hot gas. That's your hot gas at 500. It's going to be flowing inside the tubes, or no, outside of the tube. That hot gas is going to be cooled down by liquid water at 25 degrees C. We're going to look at heat exchanger now. Your liquid water at 25 degrees C is going to cool down the hot gas, which contain carbon monoxide and carbon dioxide. The ratio of the hot gas and the water is 0.2 mole of your water to 1 mole of hot gas. That's the ratio. Okay, heat is transferred from the hot gas to the water, causing the gas to cool down and the water to be heated up. Okay, now the saturated, your water is going to come out as saturated steam at 5 bar. The steam may be used for heating or power generation. Okay, we don't need that. The hot gas leaving the boiler is going to be burned and discharged to the atmosphere. Okay, that's an additional information. The boiler operates adiabatically. Okay, that's a good, that's something that you need adiabatically. All the heat that is transferred from the hot gas will go into the water. That's what it means, adiabatically. No heat is going to be escaped to the surrounding air. Okay, it's just exchanging heat. Oh my God, somebody just rang up. Okay, let me stop this. Okay, your hot gas is going to transfer its heat to the water. So the water is going to get heated up. The hot gas is going to be cooled down. That's what the system is all about. It's going to be adiabatically. None of the heat is going to be lost to the surrounding. Okay, the flow rate, you're going to assume 1 mole of what? Basis of 1 mole of what? Let's look at the question properly. 836. 1 mole of the feed gas. Okay, 1 mole of feed gas. And my phone is ringing. How can I stop it? Yeah. Okay, let's go back to that example. Now I'm going to cut this off. Yeah. We need to draw the diagram. As always, every time you have a problem, start with the diagram. Because from the diagram, oh my God, this person is trying to call me up. Can you answer, please? Oh dear. Okay, this is your diagram. I got it wrong. I need to redraw it again. I got distracted by the phone call. It's a heat exchanger. This is a heat exchanger. You're going to have two parts. I mean, the diagram inside your textbook is quite complicated. We're not going to draw it like that. Okay, your hot gas is going to flow at the top layer. It's not actually like that in the actual case. It's going to flow outside of the tube, and your cold water is going to flow in the bottom half. It will not be in contact with each other. Your cold water and your hot gas is not going to be in contact. Okay? So over here, you have your hot gas. Guys, I need to answer the phone. Can we take 5, please? Guys?
Yeah, sure,
Next
doctor.
5, please.
Sure.
Okay, thank you very much. I need to answer the phone. Okay, give me- Okay, guys. I have to rush downstairs. Okay, guys. Okay, let's start. Let's look at this example. You have hot gas. That's your hot gas. You have 8 mole percent, 0.08. Oh, sorry. I don't have enough space to write. But okay, let's squeeze everything. Let's make sure that everything can be squeezed there. 0.808 mole per mole of carbon monoxide, and the rest 92% mole per mole of carbon dioxide. The temperature is 500. That temperature is 500 degrees C. Yeah, that's your hot gas. Guys, are all of you with me? Everybody online?
Yes, doctor.
Okay. So now you have your liquid water. This is your liquid water. The liquid water is at 25 degrees C. That's given. What else? You have the flow rate. I need to erase this. Just now it was mentioned that the flow rate of your hot gas is 1 mole. You're going to have a basis of 1 mole there. Okay. And what else do we have? We have the outlet of the water is going to be saturated steam. That's going to be saturated steam. It's given in the statement at 5 bar. Okay. What else? The ratio 0.2 mole of, you are given 0.2 mole of water to 1 mole of hot gas. That's the ratio given. So this is going to be, the liquid water is going to be 0.2. I'm going to erase that because I need some space to write. That's going to be 0.2 mole of liquid water. Yeah, there you are. What else? It's going to be adiabatic, so the hot gas is going to be transferred the heat to the water. Okay. The question asks for what is the temperature of the exit hot gas. What is this temperature going to be? Previous examples, we have been solving for the heat. Now we are this example is asking for the outlet temperature. Okay, so that's a bit different. So basis, it has been stated that your basis is going to be 1 mole of the hot gas. So 1 mole of your hot gas. Okay, that is your basis. Now, how to tackle this problem? You know that the amount of heat from the hot gas is going to be, the heat transfer is going to be, for the hot gas is cooling down, isn't it? From 500 is going to be cooled down. This temperature is going to be less than 500. The outlet temperature is going to be less than 500. You know that because the hot gas is going to transfer its heat to the liquid water. So that is going to be, the hot gas is giving off its heat. So it's going to be negative. But the heat transfer to the liquid water is getting that heat from the hot gas, so it's going to be positive. But that value, the value that you're going to calculate, the value that is going to be the same. So how I'm going to write that down? Let me erase that. So it's going to be written as this: Q hot gas negative Q hot gas is equal to positive Q liquid water. There's a negative and a positive sign in front of them. Yeah? The water is receiving the heat from the hot gas, so it's going to have a positive sign. The hot gas is going to release its heat, so it's going to have a negative sign. Just like how I draw in the diagram here, the hot gas is giving off its heat to the water, so it's going to be negative. Okay, guys, that information is very important. Yeah, so now we need to tabulate. Before that, what is your reference state? So let's, before we start our drawing our table, construct our table, what is your reference state? Whenever you have steam, what is your reference state? Guys?
Zero.
At the trigger
Okay.
point.
for steam, this liquid water, remember you need to specify the phase, liquid water at triple point. You can write triple point, or if you want to be very, also you can write the temperature, which is 0.01 degrees C and 0.00611 ATM or bar? I forgot. Yes, bar. Thank you.
Bar.
Okay. That is your condition reference state for liquid water. Now you have the hot gas. You have two gases here. You have carbon monoxide gas and carbon dioxide gas. So what are you going to use as the reference state for both gases?
The inlet.
The inlet. Okay, that's one suggestion. Any other suggestion?
Or maybe the outlet, because we know the inlet temperature.
I would look at them in the table. If they are exist, I will use the tabulated references.
Table? Okay, you're going to use the appendix.
Yes.
Which is table B8. I would do that too because you already have it available. Yeah, better not use the inlet or the outlet, especially the outlet. You cannot use it because you don't have the temperature. You're supposed to find the temperature for the outlet. So you cannot use that as your reference state. You can use the inlet, that's no problem. But then if you use that as your reference state, you need to integrate. You need to use CP. So why not just get it directly from appendix B, table B8, because you don't need to integrate. Once you just get it directly from the table, or you just need to interpolate. So let me erase this first. Okay. So where is our gas that we were looking at? Carbon monoxide, carbon dioxide. Okay. The temperature that was given for the inlet, 500 degrees C. So definitely this is your CP, this is your enthalpy, that's your enthalpy for both gases. Can read it off directly from the table. But why not just use this as the reference state to be that of the same as the table? But specified the gas should be carbon monoxide and carbon dioxide. So let's go back to our example. So our reference state for both gases is going to be, again I did the same thing. It's going to be at 25 degrees C and 1 atm. Yeah. So two gases at the same reference temperature. The liquid water, you're going to use the steam table. Okay, so now let's construct our table. Not sure how many rows I'm going to do. Do I need 3? Do I need 4? Let's see, I need carbon monoxide, I need carbon dioxide, and I need water. Oh dear, I need to undo that. My line is not straight. Okay, I need to put water. Yeah, so this is in. What is the unit? We are using mole. So,
Doctor,
yes?
we have saturated steam. Should we put water as liquid and gas?
Well, it's like this. You could say this is vapor. You can say that, or you let's see. Let's undo that. Look, just put it as liquid, for example. If you want that liquid, and you have another row. Then you have water, vapor. You can do that. But if you just write water, you know water can be liquid, it can be steam. So that means when you put your inlet, you will have something there for your inlet, but for the outlet, you only have for steam, then you have, you know what I mean? If you, okay, you only have one row. Now you have an extra row, okay?
Okay.
Okay, good. So now let's just tidy this up. Yeah, now you need to fill this table. It's mole. I'm not sure it should be mole per minute or what, but the statement says mole, isn't it? So now your enthalpy in, that's another problem. And I'm going to write down the unit, because if you're going to use the appendix B8 just now, the appendix B8, the unit is going to be kilojoules per mole. But if you're going to look at steam table, which is B, this is steam table. Where is your steam table? This is your steam table. This is your steam table. Okay, that's your steam table. The unit is not going to be kilojoules per mole. It's going to be kilojoules per kilogram. Let me show you guys. Okay, that's it. Kilojoules per kilogram. So you have 2 units here. So how are you going to write it in your table?
Doctor,
Mm.
can we, after we get the answer, we divide it by the molecular weight and get all the kilojoule per mole?
Okay, you can do that. Yes, you can. Then it can become kilojoules. Oops, I did that again. You can write kilojoules per mole. Go ahead, no problem. Yeah, so this is N out. That's mole. Yeah, enthalpy out kilojoules per mole. Yeah, because we need to multiply the number of mole with the enthalpy, then you can cancel off with the unit, isn't it? Okay, coming in, carbon dioxide. Carbon monoxide. This is 1 mole. The total flow rate is 1 mole. So what is the number of mole of carbon monoxide? Anybody? You have the composition there. The
0.08.
0.08.
Okay, so that's 0.08. And the other gas, carbon dioxide, 0.92. Okay, the same thing over here, 0.08, 0.92. Okay. Next. Water. Water, the amount of liquid water coming in, you know, is going to be 0.2 based on the ratio given. 0.2. So that's going to be 0.2. Uh-oh. Okay. You're not going to have any water liquid coming out. You're not going to have any vapor coming in for water. You're going to have the same number of mole of water steam coming out. Okay, let's look at the diagram. Coming in is liquid. Coming in is liquid. Coming out is saturated steam. But the same amount of mole, 0.2, same mole. Because it has nowhere else to go. It's just passing through the heat exchanger, receiving the heat from the hot gas. So it's still the same 0.2. Okay? So now, let's look at our table B8. What is the T reference is 25. 1 atm, the same as that of our appendix. Where is my appendix? Okay, B8. Now, this is B8. We just now said that at 500 degrees C, this is our enthalpy for carbon monoxide, and that's the enthalpy for carbon dioxide. So, guys, take note of that value because I might be flipping back and forth. So, 14.38 is for carbon monoxide. That's 14.38. And what is that value for carbon dioxide, guys?
21.34.
0.34. Thank you. Thank you, Sulaiman. Okay, done. What is the value for the outlet? You don't know. Why you don't know? Because you don't know the temperature. Let's give it a value, symbol of H1, H2. But you don't know the temperature, so then there's no way. Even you have the table, but you don't know the temperature, you cannot get that value from the table. So from the steam table, you have a temperature of 25 degrees C. From the steam table, we're going to look up 25 degrees C for water. Yeah, steam table. This is bar. Where is the temperature? 25 degrees C. That's bar pressure. Okay, this is temperature. 25. Okay. Let's come across it. Here it is, 25. So where is the water? Liquid water. That's water. So if you go along this horizontally, is that the value?
Yes.
Okay, 104.8. The unit is kilojoules per kilogram. 104.8. Okay, 104. Now I'm going to write that here first. 100, ouch, again. 104.8 kilojoules per kilogram. I'm going to change that to kilomole. Okay, let's do that. 104.8 kilojoules per kilogram. You're dealing with water, so the molecular weight of water is, guys? Anybody? The molecular weight of water?
18.
Thank you, 18. So that is going to be kilomole. But we need it in mole, so we change that to mole. Cancel that, cancel that, cancel the kilogram. You will get it in kilojoules per mole. So what's the answer? Let me see. Do I have?
1.886.
Sorry, 188.6.
1.8. Yes.
Thank you.
1.886.
1.886. Okay. 1.886. Is it?
Yes.
Thank you, Sulaiman. So that's 1.886. Yeah. And you do the same thing for the outlet saturated steam. Your steam coming out is at 5 bar. Yeah. So we're going to look at saturated steam at 5 bar. Again, go back to the appendix at 5 bar. Now we'll be looking at pressure. Just now we are looking at temperature. Now look at pressure. 5 bar. Okay, I just come across it. That is 5 bar. Okay, that's 5 bar. So let's look for steam. Saturated steam at 5 bar. Is that the value? 2747.5? Is that it?
Yes. Yes, it is.
Yeah, 2747.5. So let's go back. Whoosh. Cannot keep on doing that. 2747.5 kilojoules per kilogram. Again, we change that to kilojoules per mole. Same thing, 18 kilogram, 1 kilomole, 1 kilomole, 1000 mole. 1000 mole. So, what is that in kilojoules per mole? Cancel your unit. Okay. What's the answer? Anybody give me a value? Let me see whether I have my solution here. Anybody? Give me an answer. Anybody?
49455.
Sorry, can you repeat that again, please?
49455.
49.455, is it? Nabila?
Yeah.
Thank you. Yes, 49.55. You know how you can make this life a bit easier, guys? Instead of doing the conversion from the enthalpy, how about you do the conversion using that value? That is in mole, right? So if you stick with that, change it to, oops, I don't want that. Change it to, instead of mole, this is mole, change it to kilogram. That's easier, right? You only do it once because you have the same thing here, isn't it? So then you stick with this enthalpy that you got from the steam table. You stick with that enthalpy from the steam table. You just change the molar flow rate to, the mole flow rate to kilogram. Now, what we did just now, we are doing it twice for the enthalpy. But if you do the change just for the rate, you only do it once. Just personally, I'm just pointing it out. You can save time there. Okay? Instead of doing twice the calculation for the enthalpy, but then that's a very small, just a short, maybe 1 minute of calculation. So it will not make that much of a difference. But what I'm trying to say is that you can do either and change from the unit of the enthalpy, or you can change the unit of the flow rate. Okay, the amount of mole to kilogram is either way. You can do it. Okay, let's solve. We have managed to get everything that we need except for the unknown, which this is the unknown. Yeah. We already specified, excuse me, we need this equation. We need that equation. Okay. So now, let's see. You can solve for water. Can you? Just do the calculation for this, just for water. Okay. So your energy equation just now, Q you know, you even though if you use the open system, you see open system equation, if you write that down, you will end up with the same thing. Enthalpy change plus energy, kinetic energy plus potential energy equals to heat plus shaft work. You know you're not going to have any shaft work, you're not going to have any potential energy, you're not going to have any kinetic energy. So you end up with that as your equation. Okay? So outlet, in this case, there's no dot there actually because it's just small. In yeah, there shouldn't be any dot here. Okay, that's Q, that's H. So just for water, why are we just looking at water? Because you have completed the table. There's no missing part for that, for water. It's enough already, enough information for you to calculate. So now let's do for water. Even though one of it is in the liquid phase, the other one is in the vapor phase, it's still water. So let's do the calculation. For your outlet, you have, let me use a different color now. Let's use green. Okay, that's your outlet. And that's your outlet. Yeah, so that's your outlet for water. 0.2 times 49.455. That's your outlet. Yeah. Minus your inlet. Your inlet is that value, 0.2 times 1.866. So that's your inlet. 0.2 times 1.886. So what is that value, guys? What is the unit, first of all? What is the unit? This is mole. Cancel with your mole. Your unit is mole. Time with kilojoules per mole. You cancel off, it will be in kilojoules. The unit will be in kilojoules. Okay, so what is the answer, guys?
I got 9.51
9.51.
kilojoules.
Anybody get kilojoules? Thank you. That's Aiman. So anybody else getting a different value?
Same.
Same, good. Okay, that is for water. That is for water only. Yeah, whether it's steam or water, it's still the same thing. Yeah, it's just the phase change. So 9.51. So go back to our statement just now. The liquid water is receiving the heat, so it's positive, but the hot gas is giving off the heat, so it should be negative. So that same heat that we just calculate for the hot gas is equals to negative 9.51 kilojoules. Okay, I did specify. I did mention why this is negative, because the hot gas is giving off the heat, so it's negative. So you have that same value 9.51, but you have a negative value there, and that is equals to out the number of mole and the enthalpy, corresponding enthalpy, minus in the number of mole and the corresponding enthalpy. Yeah, so let's look at our table. We have two components. We have our outlet over here. We don't know the enthalpy, so just write down the enthalpy there. Okay, so outlet minus 9.51 is equals to our outlet for carbon monoxide 0.08. 0.08 times by H1 plus 0.92, that's for carbon monoxide, H2, that's your inlet, minus your outlet. Your outlet, I'm going to highlight it for you guys. That's outlet, that's your carbon monoxide just now. This is carbon dioxide. So 0.08, 14.38. 0.08 14.38 plus 0.92, and the corresponding enthalpy for carbon dioxide is 21.34. 21.34. Okay. One equation, two unknown. You can solve it directly. So we're going to do it by try and error. Okay? By try and error. Okay, guys. I'm going to go back to that same table, because we got our value just now from the appendix B8, right? We use the same reference as B8. This is from appendix B8. So we're going to go back to appendix B8. Where is our appendix B8? Let's scroll up. Okay, there it is. Yeah, now the inlet temperature is 500. You know you're going to give off the heat to what the hot gas is going to release heat to the water. The water is going to get heated up. Obviously, it changes from liquid water to saturated steam. So the hot gas, when it exits the heat exchanger, should be having a temperature less than 500. So let's say, just for my first trial, let it be 300. So this is the corresponding enthalpies. Yeah, just say it's 300. So for carbon monoxide, 8.17. So I'm going to flick through. So guys, please help me with the enthalpies. Take note of the enthalpy for both components, carbon monoxide and carbon dioxide for me, because I'm having problem going back and forth. It will save us some time because it's 340 already. So first trial, I keep on doing this. Let's see out hot gas equals to 300 degrees C. So at that temperature, H1 is equal to what is it, guys?
8.17.
Sorry, Sulaiman?
For CO is 8.17.
8.17, thank you. That's kilojoules per mole. And for carbon dioxide, please?
11.58.
Well, thank you, Sulaiman. Okay. Now, put in both values, H1 and H2, inside our equation over here. Yeah? Don't put sorry. Let me undo that. Let me put in let's do the whole thing all over again. 8.17. Okay, put that value for there. Plus 0.92 for H2. Put that value over here. 11.57. Yeah. So this is your outlet minus your inlet 0. Guys, multiply for me that value, because I don't want to do the whole thing.
Negative 9.4748. Negative 9.48.
Negative 9. Whoa. Is this negative 9.48? No?
No, I mean the final answer.
Okay, Okay, I need to rewrite everything then. Okay, I was trying to skip that process of writing everything. That's why I asked for the answers. So, okay, let's do everything all over again. Repeat the inlet value, the calculation for the inlet, 21.34. So, okay, Aiman, what did you get? Negative 9.48. Thank you. That's no way close to that answer. This is the answer, negative 9.51. This is negative 9.48. That's not the correct answer. Okay, so that means your temperature at 300 is the wrong answer. So let's do a second trial. So this is your first trial. Your second trial. It must be maybe somewhere lower than that. Let's hot gas, the gas temperature outlet be, let's look at our appendix again. The value, let's it be, give it another color, red. Okay, 200. If it's 200, this will be 5.186, 7.08. Please take note of the enthalpies at 200, because I need you guys to tell me the values. And now let's go back. At 200, God, I keep on doing that. 200 degrees C. So H1 is equal to, somebody please give me the value.
5.16.
5.16. Thank you, Sulaiman. That's kilojoules per mole. From the table just now, H2.
7. And for CO2 is 7.08.
08. Thank you. Kilojoules per mole. Yeah. These values is from this table just now. Just for those who are lost, that's the value from the table. Yeah. So now, putting in again the same into the same equation, 0.08, 5.16 plus 0.92, 7.08. This is your outlet minus your inlet, 14.38 plus 0.92, 21.34. Yeah, so what's the answer? Negative?
13.9.
13.9. Okay, that's far off, isn't it? That's
Yes.
very far off. So now what we're going to do, we're going to do interpolation. Yeah.
Doctor,
Yes.
can we assume that it's just like 298 or 295
Do
degree?
not assume. You need to calculate. You need to do calculation. Okay.
Doctor,
Yes.
this one, in the test or it will in the exam, it will waste time, right? I mean,
Yes, it will
the whole of
all
this,
the time.
it will take a lot of time.
Yes.
I mean, like trial and
Yes.
error.
It has to be.
So how is it like? I mean, like, are there questions similar to this? I mean, that.
Yes. Previous year final, yes. They do have
So
it.
is there a trick that you can do like to find it quick?
No.
Is that, I mean, like,
No, you just have to go through this whole thing. Let's see, negative 9.51, negative 9.51. Okay, you need to find that temperature. What is T out? Just interpolate. So what is the actual temperature T out for your hot gas? You just have to do it by trial and error. Unfortunately, well, we will make it easier by setting the range for you guys to guess. Maybe we say between 300 to 200, maybe we can say, so that you don't have to go too far off, So you have a range of temperature which you can do your trials. So in this case, from 200 to 300, only twice the trial. Yeah, we're not going to do 5 trials. We'll try to save you having to go through all that number of trials. So anybody, what's the temperature?
I got 299.3.
Yes, that's the final temperature, which is the same as the textbook. The textbook, the answer for that example 836, the answer is 200 and where is the answer? 299. If you are using the third edition, the page number is 377. The problem, this example, if you look at your textbook, has been solved using integration. We did not solve using integration. We solved using appendix B8. That makes it a lot easier. If you solve it using the same method as the textbook, then you have a problem. Because the textbook, what the author did for this example, the author chose the reference state as 500 for the hot gas, the inlet condition. When the author did that, automatically the author will the work will be done using integration. Yeah. When you choose this as your reference state, then you need to do integration from 500 to a certain temperature. That temperature is that outlet temperature. You have to do CP. That will make it very complicated. Any questions? Any question? Guys? It doesn't look that difficult when we solve it using table B8 because you have just to do the trial and error. Even though when you are doing the CP, the integration, you still have to do trial and error. You just have to plug in the temperature inside the equation. Still trial and error. There's no way of getting the answer directly. Any questions?
It's clear, Doctor.
Thank you. Thank you.
Doctor,
Hmm.
I didn't understand the CP part.
Okay. If you look at this question, if you set your reference state for the hot gas is equals to 500, which is the inlet, okay? So that means for carbon dioxide and carbon monoxide, you set your reference temperature to be the inlet, then you have to calculate your enthalpy for this enthalpy, that enthalpy, and this enthalpy. You have to calculate using H equals to from 500 degrees C. From that is equals to what? 500 to 500, isn't it? Isn't it? Because that in the inlet, you set that as your reference state, right? Okay, let's put it another way. If your reference state is the inlet, what is the enthalpy of That H is what? And that H is what? For both gases?
0.
0. Okay, fine. You don't need to integrate. But for that temperature, you don't know, right? So that means for H1, you get to integrate from 500 to that temperature using Cp of carbon monoxide dt. And for H2, you need to integrate from 500 degrees C to T or Cp of carbon dioxide. You need to do that because you don't know what temperature. For this, for the inlet, is easy because they are both at the reference state. So both values of the enthalpy is 0. But for the outlet, you don't know the temperature, so you need to integrate. So you need to use appendix B2. So that means for this part, you will get A times 10 to the power minus 3 plus B times 10 to the power negative 5 T plus C times 10 to the power negative 8 T squared plus D times 10 to the power negative 12 D to the power 3. Your answer will be in that form.
But doctor, we won't do like trial and error, right?
Yes, you still have to. Because you will put in the values for your temperature. Okay, for these temperatures, you need to put in the values. And you make sure that the whole thing will turn out to be minus, what was the answer just now? Minus
9.5.
9. Yeah. So it's very important. The reference state is very important. If you're going to choose, if you choose the reference state to be, as the inlet condition, then you have to do integration. But you still cannot get the answer of T directly. You still have to do trial and error. There's more work there because there's T to the power of 2, T to the power of 3. There's more work there. But if you use appendix B8 as the reference state, whereby you can get the values directly, it's just putting in the value that you get from the table inside the equation and see whether it turned out to be negative 9.51. That is far easier than using the integration.
Doctor?
Yes.
I think we won't have to do a trial and error because if we do it in the calculator and say that this equation will equal to negative 9.51, is there a possible way like it will show us the second temperature, right?
I'm not sure whether you can do it directly because when I read through the solution for this example, because they did it using integration, I saw somewhere that said that the solution is by trial and error. Yeah, it did. The author say our goal is to we could perform the trial and error search manually, but if the spreadsheet program has a goal seek tool, then if you have a spreadsheet, then it might not be a trial and error. Maybe it can do that using your calculator.
Right. Thank you.
Okay. Maybe you should try doing it using your calculator.
Okay, I'll do.
Okay. Any other questions? Guys, this is quite a long example, but it's very interesting because, it is the concept of heat exchanger. The concept of heat exchanger, the heat flow from the hot gas into the cold liquid water. You need to know the fact that one of it is going out, the other one is receiving the heat. So there's a negative sign for the heat loss from the hot gas. You need to know that. But if you don't put the negative sign, well, there's no way you're going to get the answer correct. Okay, guys. Any questions? Anything? It's already 3:53. So this example really illustrates how we need to construct the table. Get the correct reference state. If you have the data available, then use it. Okay. You need to use your general equation, energy balance equation. If it's an open system, use for the open system. If it's a closed system, use the closed system equation. Okay, guys. So if there's no question, that's it for today. We're going to have one extra class tomorrow at 2 p.m. in order to make up for the last week Sunday that was cancelled due to the holiday, Bali holiday. So we're going to continue with chapter 8, but we're going to look at when there is a change of phase. Right now, we do not look at it because we're just heating up and cooling down, that's all. But once you have a change of phase, then it becomes more complicated. Okay, guys. Thank you very much.
Which means we're gonna use the hypothetical
Pass.
concept
Yes.
a lot. Yeah.
Yes. Yes. We do.
Uh,
Yeah.
Sir, can you display the QR code again?
Sorry.
The QR code.
Oh. Okay. Thank you for reminding me. Let's go back to the QR code. Not sure why you can there's no internet. What do you mean there's no internet? I'm already got. Why is there no internet? Don't tell me I have internet because
maybe
I'm
doctor,
online.
you can try to refresh your browser.
Okay, refresh my browser.